Yeah, the thing is that but I mean, I think the principle is easy to understand, but then when you actually go and if you want to figure out the size of that variance and how do you do the maximization, then you need to basically determine like this thing called a covariant matrix, and then after that you need to do singular value decomposition of that matrix, and that's how you calculate the variance of that, like maximize that. The principle is not difficult, but the mechanism is, the way to calculate it requires a bit of math. And you don't need to worry about that. You just need to understand what's going on. So the next one is K-means clustering. So K-means clustering you'll hear a lot about. So there are many ways to do clustering. There are also deep learning methods to do it. But K-means, this helps you sort of visualize how clustering happens. And this will kind of give you an idea as to how to form form patterns. So one of the things I want to show you is that the two are related when you think about it. So in this case, as I talked about, this is about reducing a high-dimensional space into something that's visualizable. And the next thing you do is you apply K-means analysis or clustering, and the K-means clustering will then pull out the clusters that are there in your data. So this is a way for you to kind of visualize how my data is segregated. So bring the high-dimensional data into something that you can visualize, and then apply K-means to that, and then you can see whatever structure or whatever clusters. For example, you want to do customer segmentation, that would be a good way to visualize it, that my customers are somehow segmented in this way. Does that make sense? So this is essentially what K-means will do, is it will take your high dimension. So firstly, you do PCA analysis, and that'll essentially take you from your high dimensional space into a two-dimensional, for example. The next thing you do is you perform K-means, and that'll kind of like identify how things are grouped together. And when you calculate that, then that'll kind of give you, for example, if you want to do customer segmentation, that would be a good way. So each one of these points represents a customer. So the customer will have a whole bunch of variables associated with them. They could be age, they could be what location of the city they come from, it could be income, it could be sex, it could be a whole, like, previous purchase history, could be a lot of different factors. Yeah, exactly. So you have all of that. So each one of these points exists in a very high dimensional space, because each one of those are features of your customer. And what you first do then is you reduce the size of that space into 2 dimensions. You don't know what those 2 dimensions represent. Some abstract value representation of these high dimensions, and you don't care, because what you're doing is you're preserving that information from the high dimensional space to the 2-dimensional space. Now each one of these people represents a customer, and so then what you want to do then is you want to figure out, okay, well, how are these customers grouped together? With the cosmetics thing, for example, when we did the clustering thing, we noticed, for example, that there are 2 clusters that started to form, and it turns out that one of the clusters represented mothers and the other one represented daughters. So their daughters would be buying like these really bizarre types of lipstick, and their parents would try and get them to buy more conservative stuff. So they ended up with this really bizarre mix. So that was, they could figure out that there were 2 customer segments from that. And so that would be kind of like one way to do that. That's also how you can, for example, if you, for example, notice a shift in sales patterns, that's like you notice that the previous months, this is what sales look like, and then suddenly you notice a significant shift in terms of how the values have changed, then that would be a way to kind of like, that's how you do this. Okay, so this is a much simpler concept than PCA, and so I can just illustrate it and then kind of show you sort of what the basic principle is. So I know I'm going through a lot of more complex stuff today, so just just learn the basic principles. You don't need to worry about the details. But this is all useful when you want to, when you look at, when we show, for example, some of the machine learning architectures, it helps you understand a little bit about what's going on, and kind of when I talk about things, it makes sense. So suppose I have, okay, this is a really stupid example, but I have, let's say, 10 points. So So I have 10 points there. Now visually, you can see that there's a cluster. You kind of imagine what a cluster might look like. So the question is, how do you calculate what those clusters are more exact, in a more exact way? Well, the first thing that you do is you calculate, you figure out, you pick 2 points. They're called centroids. So this is C1 and then C2. So what you want to do now is you want to kind of group the points by how far they are away from your centroid. And so you can see that these points go together, obviously. And these points will also go together because these are the closest to these 2 centroids. Now, in this case, I have already I've sort of already given that, sort of have determined that. But basically what you're trying to do then is you're using, what you want to try and do is figure out the centroid, like the true value of is to kind of shift that centroid so that the distance between each of these points is then minimized. So right now it's not minimized because, for example, this is really long and this is really long, so maybe the right value of the centroid is something here, because then when so C1 prime, because that sort of makes sure that all the distances, it's very hard to see, but all the distances have been minimized. So if you sum over all of these distances, you're reducing that amount to the lowest amount. So the goal that you have is to figure out, let's say I want to figure out, okay, let's look at 2 clusters, and I want to then figure out what the centroid is. I then try and figure out a point where it minimizes the distance between the points together.
And the centroid is based on the locations of the two-dimensional space.
It could be whatever dimensional, as long as, like, it could be 3 dimensions if you choose, like if you reduce if you're looking at three different features. Like, it depends on how much you've reduced it.
But it's not on the original data set, it's on
it could be the original data set if you only have 2 dimensions, right? So if you...
Okay, all right.
Yeah, so...
Could clusters have unequal sizes, or do they all have to be the same size, like amount of units in it?
So no, they can have different sizes, and so it gets more complicated, and I'll kind of but yeah, they can have different sizes. So basically, as we see, this is kind of exactly what we're doing here. You have the components of these. So you have a set of centroids. And for each of these CJs, you want to kind of like take some value k, which is called Kmeans. And what you're trying to do is you want to figure out, okay, well, what is the distance between that and each of these points? And then you want to minimize that. So that's that's what I just described. And then what you're trying to do then is you keep adjusting that. So you randomly initially start with that. And then for each of those, you assign an xi to one of the clusters, and then you recalculate the cluster, recalculate the centroid, and then keep doing that over and over again until you have the right amount. So what is the one issue with this? The one issue with this is that if I have these points, in this case it's pretty obvious I have two clusters, but this doesn't tell me how many clusters I have. I could have easily picked 3 centroids, or 4 centroids, or 10 centroids. The problem with 10 centroids, at that point, every point belongs to its own cluster, which is meaningless. And then if you have 1 centroid, then all the points belong to just 1 cluster. So you want to figure out a case where you have the right balance, where you have the right mix of points and in terms of distances. So the way you kind of do this is that you have something called an elbow point. And so this is kind of like the mean distance to the centroid. So what you're trying to do is, this is the number of centroids that you have, and these are the mean distances between the centroids. And so what you're trying to do is that you'll keep adding, so let's say I start off with just 2 centroids here, and then I add a third centroid, C3, and then kind of keep working on that. Then what will happen is that inevitably the distances will keep dropping until the distances are equal to 0 when you hit, if I have 10 centroids, then each point is a centroid. So it'll eventually hit 0. But there is a point where it starts to flatten, and so you have this kind of curve, and the point where it starts to flatten is called an elbow point, and that is the optimal number of clusters, and that is the value ultimately that you choose as determined. That's how you'd cluster out your set. So the way you have to do this is, in some case you can eyeball it like here, but in some cases where it's more complex and you want to figure out what is the right number of centroids, you have to play around with it, and you have to kind of work out a curve like that. And then so try out with different k values until you figure out what is the right, the optimal number of clusters there. Make sense? So yeah, that's the way it is.